Hello everyone, and our project is deep slope estimation with formal verification. I'm Yujia, and this is Lucy, and our advisor is Professor David Hao. And yeah, we use normal estimation to represent the slopes and the condition of the road. Like this is our result of the normal estimation on the KD data set, and the direction of the arrows represent the direction of the normals. Like you see, on both sides of the road, like on the walls of buildings, the direction of the normals should be in a horizontal direction, and like on the road, the direction should be pointing upwards. So the results seem to be pretty good. And the motivation of our project is to determine which part of the terrain are drivable for autonomous vehicles. And actually, normals actually provide important features for a lot of other tasks, like point-based rendering or like surface reconstruction. So actually, our project could be used in a lot of other scenarios. And the method we use, the pipeline is we first estimate normals with deep learning methods, and then we do model compression. And note that in our title there is a formal verification part, and this part is actually done by another group. But formal verification actually requires the model to be pretty small. So our mission is just to compress the model as much as possible. And the solution is we try some normal estimation networks, like PointNet, PointNet++, and we also tried several model compression techniques. Yeah, Lucy will show our past works.
Here's some of our past works. We did something about data preparation, and also we have some experimental results from deep learning methods. And first about the data set. One of the challenges is that we need to figure out ways to get the ground truth normals. So we first use some generated data where we randomly generate planes and curvatures, where the ground truth normals can be directly calculated from their expressions. And also we can add Gaussian noise manually to the data and to test the robustness of our models. And since our final goal is to predict normals on self-driving vehicles, it's a real-world application. So we also use real-world data sets like KD data set. We selected 4 categories from this data set and randomly sample patches from the full sync point clouds. And each point cloud has 4096 points. That's the data process we used in the past. However, this process has 2 main problems. First one is that the unit of the sample is different after we do the normalization of the small point clouds. And also, second is that the data is not clean. We can see that in some parts of the point clouds, the points are pretty sparse. Like these 2 sides of the sample point clouds, and these points may be of less use, and they are maybe just noises. And we will show in the present work how we fix this problem. Here's the model we use to estimate the normal. Here's the modified version of PointNet. And we do 2 main modifications. The first one is about the input transformation network. Since PointNet originally is not designed to solve the normal estimation problem, so the input transformation network, it basically will generate a random matrix, 3x3 transformation matrix for the point clouds. And the random transformation matrix will destroy the normal properties of the point cloud. So we constrain the transformation matrix to be only rotation matrix that can help us generate good normal estimation results. And also the second one is that we modify the segmentation network of the PointNet. After we extract the global feature, we further pass this to MLP and then get a kind of like a compressed version of global feature. And we copy this n times 1024 matrix to form this big matrix. By doing this, we want this a new architecture to capture more local properties of the point. And after forming this big matrix, we then put this into this the same MLP structures as before, and output our predictions. And here's the loss function we use. It's a squared value of 1 minus the absolute value of cosine angle of the process normal and the predict normal. And here are some results we got last time. This table shows the test RMS angle error in the unit of degrees. And from the table, we can see that .NET++ in general performs better than .NET. But its inference time is a little bit lower. It's slower than .NET. And but this inference time is the time on one point cloud, and there are 1496 points in the point cloud. And here are some visualizations on the generated data set. These are two random curvatures. We can see that the results are pretty satisfactory. Also here's some results on Kitty dataset. From the first table, we can see that .NET++ is still a little bit better than .NET, and by tuning the radius, we can get our best model of 25 RMS angle error. And however, .NET++ has some problems. First is that we can see that the inference time is pretty like double time compared to .NET. And also, we need to tune the radius very carefully to get our best model. And the third one is that .NET++ is still too big for the formal verification tools. And it's very difficult to do model compression on .NET++. So we decide to use .NET as our baseline and further do model compression on .NET. However, .NET has its own problem too. .NET, we can see that in this visualization, it's the result from .NET. We can see that in the some of the regions, these points are almost predicting the same direction. It's because that .NET it predicts based on a whole point cloud, and it doesn't have a hierarchical structure like .NET++. So that's why it's a little bit worse, has a little bit worse results. And we will show how we fix this problem in our present work.
Now, these average errors look really huge, 30 degrees, right?
Yeah, and here's a histogram. It's like in PCPNet, the paper, the RMS angle error in gray is also like about 20, and their results are pretty good. It's like 15 to 30, around 20 degrees.
I mean, when you say results are pretty good, 20-degree error is pretty bad.
Yeah,
but results are good.
In PCPNet, they compare their results with different models, and their results are the best, and their results are around 20 degrees.
When you say different models, are you deep learning?
Yeah, they compare with deep learning model and the geometry-based model. And since in real world data there are a lot of noises.
This is all the LiDAR?
Yeah.
Wow.
We will show more visualization results. When plotting out, the results seems pretty good. Since there are a lot of noises like bushes or buildings in the point cloud, but on general like walls or roads, the results are pretty good. Yeah. And here's the histogram of the RMS angle error. You can see that most of the errors are around 20, it's about 15 to 30. And we will show more visualization results later.
Yeah, so here is our present works for the past month. And first, we mentioned that for the previous data processing procedure, there are some problems. The first step is that the unit for each training sample is different. And the second is that there are some many noises we didn't handle. And the third is that the point net problem we mentioned earlier. So, and the second thing we do is we try some weight pruning and retraining, and we also try some knowledge distillation works. And for now, we are able to compress 90% of the model with comparable accuracy. Why 90% is so large? That we'll explain later. So this is how we process the data for now. Like we put the full scene point cloud in the cube. The cube is computed by the mean and max hardness value of x, y, z hardness. And we divide the full scene, the full cube, into small grids and mobilize the data inside each grid. So the point, the very small point cloud inside each grid is our training samples. So for now, the problem is how do we compute, how to decide the grid size. So there are basically two criteria on choosing the grid size. The first one is it should have enough receptive field. Like each point should have enough neighbors to compute the normals. And second is that the grid should also be sufficiently small. Like in the point net results we showed earlier, like point net we compute the normals based on too many neighbors. So this is a problem. So we force the network to only look at the very small region of the neighbors. Yeah. And this histogram shows the number of points inside each grid. Like the number of points inside each grid, it's mainly range from 20 to like 40. And after we try different settings, we use grid size of 3 meters and 30 points inside each grid. Because we want to use batch training, so the number of points inside each grid should be the same. Like if the number of points is smaller than 30, we pad with duplicate points inside this grid. And if it's larger than 30, we just uniformly, randomly sample 30 points. And if it's smaller than 15, we just discard this grid because we just deem this grid as noisy or very sparse and useless grid samples. Yeah, and in this way, like we are redefining our task as estimate normals over only 30 points, which enables us to use much smaller networks, which is required by formal verification. Yeah, and because the task becomes much easier, so our model can be compressed to a very large extent. And here is the weight pruning result. Say the blue column represents the model size. Yeah, and the first column is the original model. And the red line is the RMS angle error before retrain. And the yellow line is the RMS angle error after retrain. You can see that in this model 6, we can achieve comparable results even with only 10% of the parameters of the original model. And here is some qualitative result visualization of model 6 with only 10% of the model. Yeah. Even if some direction of the normals are like slanting to some directions, but on the road, on the walls, generally it's acceptable.
It's all slanted even on the road, right? It should be vertical.
Yeah, it should be vertical. So this is a problem with the very small model. We're working on
So
it.
a bigger model just corrects that.
Mhm.
Is that what you're saying?
Yeah, this is a small model.
I know, so the bigger model corrects it to vertical.
It's better than this.
Better than the price.
Yeah. And we also try some knowledge distillation works.
Yeah, we also try knowledge distillation to do model compression, where we use PointNet as our teacher network and Singer network as student network. By Singer, it's demonstrated in this figure. By Singer way means that we reduce the number of nodes in each linear layer to 1/4 of the original number. Here's how we train our student network. we borrow some ideas from the FitNet, and we define our hint loss as our hint loss is that we first extract the global features from TeacherNet and the StudentNet, and then we use MSE loss of these two global features. The dimension of these two features is unmatched, so we add a linear layer after the student network to make the dimension match, and then calculate the MSE loss, and use this as our hint loss. And you first use hint loss to train the previous layers and these added linear layer. And after several iterations, then we use the loss we mentioned before to train the student network, all the parameters in the student network jointly. And different from the FreeNet paper, we didn't use the output from the teacher network, since it's kind of like a regression problem, but in the FreeNet paper, they are dealing with a classification problem, so it's kind of different. In regression problem, the output from teacher network is not of that use. It's not that useful. And here's the result we have. By defining the student model, we can see that the parameters is only 2.5% of the original teacher model. While we lose a little bit accuracy, and the accuracy now is around 40. We can see that the inference time of the student model is pretty low. It's only 3 million seconds per batch. Further work may include that we will define a thinner but deeper student model, which may get better results on prediction. And here's our timeline.
Yes, we may tune the models more carefully and get better results and wrap it up, and hand in to the formal verification team. And the next step is they will just adapt their formal verification tools with our model. And at the beginning of next semester, actually there are some ideas that was trying in the commons. Like when computing the normals in the PCA process, you can use eigenvalues to weight the ground truth normals. And we can also try other ways to generate the ground truth, like match fitting. And we can also try some other models. But actually, as last time we discussed with Professor David Howe, in the next semester, we may change into another topic, because actually the next step for this topic is basically need to be done by the formal verification team, and we will just mainly discuss our model or process with them. So we may change into another related topic, but it's not set yet. Yeah, so this is generally our question.
Okay, the questions from faculty, PhD staff.
So these point clouds are all LiDAR, right?
Yeah, well done.
And so there must be, if you look at your receptive fields, are they actually sort of concentric? Do they get these samples in that concentric field? You've seen LiDARs, right? They're all like this, right?
Yeah.
They're all taking a curve.
It's a curve. Yeah, it's a circle.
It's a circle that's intersecting with a surface, right? So nobody has done, continuous discrete differential geometry analysis of a point and continuous circle intersecting a. So there must be an easier way of estimating normals from the sample. So it's not just directly, okay, let's throw it into a deep network. It looks like if you saw that your deep method has some receptive field that looks like that would be great, because it's sort of learning the sampling distribution of this LiDAR, right?
Yes.
If I use Kinect or something to create a point cloud, it should be different.
Yeah, just
The patches that they use to estimate normal, right?
Yeah, we may just.
It would be nice to see if you figure out which samples it actually used to estimate, right? So dig deeper a little bit into your network to see if it actually learns something about the sensor itself.
Okay. Sure.
is there any simple way to know which data point is from road, which data point is from street?
No.
We're just predicting.
Yeah, there is no labels on the data.
So, I was thinking, if you want to make the model small enough, and there's always limitation of its model power. It's better to convert the resources to what you really want. For example, in this case, you definitely want to know what is accurate on the road and on more. You don't want to spend any computation power of the model to the tree. If there's a simple way, for example, the location of the location coordinate, the vertical coordinate of the point, is there a simple way to rule out some points that are not so important for flow?
You mean like segmentation or something?
Yes, a simple rule to segment out those points, and then when you are training your neural networks, it's better to assign higher probability, sampling probability to those samples using mixed batches. So then you can get much accurate estimation on the road.
Yeah, I'll think about it. But one thing is that I think the real world scenario is quite complex. Maybe there is a tree stump in the middle of the road. So if I remove that, so the car may just crash with the tree stump.
That's still, you don't need to consider anything about like the 2 meters.
Yeah. That's correct. Yeah.
Does the LiDAR give you correspondence of, however many lasers it has? Does it give you correspondence of which pixel produced which, so you know which circle? Does it give you?
We use KDS.
No, but I mean, that would be very useful to do because you have a circle plane that intersects everything. So
I just didn't find this information.
yeah, but that should be available. But no, but I'm saying it's for LiDAR, it should be able to give you that knowledge. Maybe the companies that will bring that out or something. It should be ID of the laser.
Yeah.
It would be very useful.
Yeah, actually
It gives you the plane.
there are some papers
Using that. Yeah, it seems to me that that's a very powerful constraint to use.
Yes. Some geometric papers, they just use this kind of the idea of the scan is the LiDAR.
Yeah, that should be a very good way of generating knowledge.
Just didn't find it in the KD data set.
Huh?
Didn't find this the ID in the way of the KD data set.
Oh, yes, I see. Yeah, we should go back and see.
So the 0.9++ paper does a classification task, right? And how do you take it for normals and how accurate is the normal? Like, where do you get the ground truth?
The ground truth we generated use a geometry-based method.
Also, we are using geometry-based methods and supervision.
Yeah.
Yeah, this is actually the problem. There is no label.
There is no label
or
for the
estimation.
normal city data.
Yeah. So actually, the error like 30, like 20, we cannot say is the real error because we don't know if the geometric method is the correct.
I mean, geometry might not be very accurate because in a data, like when you do the geometric method, I see like a lot of errors in the normal estimation.
Yeah, same. So we are just visualizing the quality result and see if it's acceptable, rather than just depend on errors.
So, I just want to have an idea of how these things degree error is. So, but now you guys not thinking of it just like take the points where you know more or like giving a grid and UPC on that. It should give you normal accuracy. Right? How do you have any experiments on such simple basis as that? It should provide a bunch of these geometry projects. Like if you take points within a normal or grid and just do UPC fitting in that, that would be good. That would be good. Normal accuracy.
Oh yeah, that's the way we generate the ground truth.
Oh, okay.
Yeah.
Oh, it's so simple.
Yeah.
Oh, okay.
Any other questions? Okay, thank you very much.
Thank you.